So I have the matrix A, 1, 1, 0. This is 0. 0, 1, 1. I want to do a singular value decomposition of it. So A is equal to U sigma. This is a sigma V transpose, where U and V are orthonormal. So they contain vectors that are orthogonal to each other, and all vectors are of length 1. So they are normalized. And sigma contains the singular values. Yes, so I will. So I have a 2 by 3 matrix. So m is equal to 2. So m is the number of rows, and n is equal to 3 because I have 3 columns. Yes, so I can either take A transpose, or A transpose A. I will choose. I chose to take A times A transpose because if I do that, I get a 2 by 2 matrix. While if I do A transpose A, I will get a 3 by 3 matrix. So it will be easier to find the eigenvalues. Yes, so if I do A times A transpose, but of course you can do A transpose A. It doesn't change anything. It's just a bit more. It takes a bit more time. Yes, but still, I mean, you can do it. It's just A times A transpose. It may be quicker because we only have a 2 by 2 matrix and not a 3 by 3 matrix. Yes. So if we do A times A transpose, if you find it, you get the matrix 2, 1, 1, 2. Yes, and so now we will find the eigenvalues of this matrix, remembering that the eigenvalues of A times A transpose, the non-zero eigenvalues of A times A transpose are the same as the non-zero eigenvalues of A transpose A. Yes, so if we find the eigenvalues, if we solve that, we get so the determinant of A times A transpose minus lambda I, where I is the identity matrix. This should be equal to 0. So we get 4. I mean, if we solve that, we get 3 minus lambda times 1 minus lambda is equal to 0. And so lambda 1 will be 3, and lambda 2 will be 1. Yes, and so those are our eigenvalues. So our singular values will be the square root of those eigenvalues, because remember that lambda I is equal to sigma sub I squared. So sigma sub I is equal to the square root of lambda sub I. So sigma sub 1 will be the square root of lambda sub 1, so the square root of 3. And then sigma sub 2 will be the square root of 1, so simply 1. Yes. And so I will find my eigenvectors U. Okay, U because I have the matrix A times A transpose. If I had calculated A transpose A, I would find the eigenvectors V, because remember that for A times A transpose you find U, and for A transpose A you find V, basically. Yes. So if I find the eigenvectors U sub 1, that will be so for this eigenvalue here, I will get the vector 1, 1 times 1 over square root of 2, so that will normalize the vector, okay, because remember U is orthonormal and V also, so the vector should be of length 1, so I have the vector 1, 1, and now I need to normalize it, so I divide by its length, so I get 1 over square root of 2 times the vector 1, 1. And U sub 2, so the second eigenvector, this time associated to the eigenvalue lambda is equal to 1. I will get 1 over square root of 2 times the eigenvector minus 1, 1. Okay, so minus 1, 1, and divided by square root of 2, so it is normalized. Yes. So my matrix U will be 1 over square root of 2 times the matrix 1 minus 1, 1, 1. So just this is U1 and this is U2. This is U1, this is U2, and this is the normalization. Yes. And my matrix sigma, remember this has the same number of dimensions as A, so A is a 2 by 3 matrix, so sigma will also be a 2 by 3 matrix. My first singular value will be square root of 3, okay, sigma sub 1. My second will be 1, so square root of 1. I fill in the rest with 0, and also the extra columns or rows that eventually that I would have, I just fill in with 0. Okay, so I have 0 here. And remember, you put the singular values in from the biggest to the smallest one. So square root of 3 comes first, and then square root of 1. Yes. Okay. Yes. So the biggest value first. Yes. So now I have found my matrix U. So now I can use the shortcut if you want to find my vectors V. So remember that V sub I is equal to 1 over sigma sub I times A transpose U sub I. And just by the way, U sub I, it works in both ways. It would be U sub I is equal to 1 over sigma sub I times A times V sub I. Yes, that would be the opposite you will. Yes. So if you use this formula here, remember that it only works for the non-zero singular values, but here we we only have two singular values, and they are both non-zero. Yes. So we have v sub 1 is equal to 1 over sigma sub 1 times A transpose and u sub 1. So if we do that, we get wait just a minute. We get 1 over square root of 6 times the vector 1, 2, 1. Is that correct? Wait, let's just see. We get like 1 over square root of 2 times 1, 1. That's my vector. A transpose, so I have 1, 1, 0, 0, 1, 1. And I have 1 over square root of 3. Okay, so this is the 1 over sigma sub 1. So that is 1 over square root of 6, which is in fact correct. And I get, if I multiply this vector in this matrix, I get 1, 2, and 1. Yeah, so in fact this is correct, yes. Yes, and it is already, this is 1 here. Shit. Yes, so this is my vector v sub 1, and it is already normalized because the square root of 6 is the length of this vector, so square root of 1 squared plus 2 squared plus 1 squared, so square root of 6. So this is already normalized, yes. Now v2, if I do the same thing, 1 over sigma 2 times A transpose times u sub 2, I get 1 over square root of 2 times the vector minus 1, 0, 1. Okay, so again, this is also normalized because square root of 2 is the length of this vector, so it will be, the length of this vector is square root of minus 1 squared plus 0 squared plus 1 squared, so square root of 2. So this is also normalized. But now, remember that if I have an m by n matrix, U will be a m by n matrix, where m is the number of rows of A, so here 2, and V will be a n by n matrix, where n is the number of columns of A, so here 3. So my V should be a 3 by 3 matrix. So I in fact have 3 rows each time, but I need a third vector V, okay? Because I said I have a 3 by 3 matrix, so I will have like V1 here, V2 here, and now I need a V3, okay? So we already found our two singular values, so we cannot use this formula. And I said if we had a third singular value but it is 0, we could also not use this formula. So we need to find a vector that is orthogonal to those v2 and v1. So orthogonal to all those vectors v we found now, and then we will need to normalize it. Now, luckily, we are in 3 dimensions, so we can simply use the cross product. So we take the cross product of v sub 1 and v sub 2. Remember the formula for the cross product. Look it up otherwise. I mean, I think you should know it by now. And so if we take the cross product of those two vectors, I get 1 over square root of 12 times the vector 2 minus 3, 2. Yes, so this is a vector that is orthogonal to v sub 1 and v sub 2. Now, this is equal to v sub 3 prime and not v sub 3. Why? Because this is not normalized, okay? The length of this vector is not 12, but 17, okay? Square root of 2 squared plus negative 3 squared plus 2 squared is square root of 17, not square root of 12. So what I do is simply I replace the square root of 12 by the square root of 17. Okay, remember, we need it to be normalized, so we divide the vector by its length. So we can simply replace the 1 over square root of 12 by the 1 over square root of 17, because at the end, I mean, it's the same thing. You just need a vector that is normalized. Yes. So this is our third vector that is now orthogonal because we took the cross product, so it is orthogonal to v sub 1 and v sub 2, and this normalized. Yes. So now our matrix V sub 1 is filled in with the vectors v sub 1, v sub 2, and v sub 3. And again, those are the v sub 1, v sub 2, v sub 3 are the eigenvectors associated to the lambdas here. For the matrix A transpose A, okay? We found the eigenvectors U sub 1, U sub 2 for the matrix A times A transpose, and the vectors V are the eigenvectors of the eigenvalues of A transpose A, not A transpose, okay? Really remember that. If you do A times A transpose, you will then find U, and if you do A transpose A, you will then find V, okay? Yes. Yes, so I have my matrix V, I have my matrix U, I have my matrix sigma. So now I can write A is equal to U sigma V transpose. So the matrix U has the vectors, the eigenvectors U sub 1, U sub 2. So yeah, here. here. So here's the matrix. Sigma, so we have sigma sub 1 and sigma sub 2, and the rest is filled in with zeros. Again, the matrix sigma has the same number of dimensions as the matrix A. And then we have V transpose, so V is, as said, this matrix here with the vectors V sub 1, V sub 2, V sub 3, which are again the Eigen Vectors associated to the eigenvalues of for A transpose A. And so we have it here, and we take the transpose of it, yes. So you can plug in the values if you want, and compute the whole result. But that's, you just plug in the values, that's what we did. So yes, we have U, sigma, and V transpose. And so just remember, so what we did is we found the eigenvalues, then the eigenvectors, depending on if we found first A transpose A or A transpose, then we use those shortcut formulas, and then it happened that you need an extra vector, but you don't have any more singular value, or it could also be that you have a zero singular value. But so here we are in 3 dimensions, so we can simply take the cross product to get our orthogonal vector, and then we normalize it, and we get our third vector as expected. Otherwise, you can use, for example, Gram-Schmidt if you want. But I have never really used Gram-Schmidt, so Or if you are, as I said, in 2 dimensions, if you have the vector AB, you know that in 2 dimensions the vector orthogonal to the vector AB is, for example, negative A and B, negative B and A, or B negative A. Yes, remember that for 2 dimensions. Otherwise, use Gram-Schmidt or find something else. I don't know. Yes. And so that's what we did. So we found the values, and then you have our singular value decomposition. Also remember that the singular values in the matrix sigma are ranked from the biggest to the lowest one. And you fill in the remaining columns or rows. If you don't have a square matrix, we fill those with zeros. Yes. And remember, U and V are orthonormal, so the vectors inside are of length 1 and they are orthogonal to each other. That's why we needed to take the cross product here. And if A is a n by n matrix, M is the number of rows and n of columns, U will be a n by n matrix, so and V will be a n by n matrix. Yes. Those are in fact square matrices, U and V. Yes. Square matrices, they have the same number of rows as columns, right? That's what I mean, yes. So that's it. I hope it was helpful, and I hope you could understand it and that you could also read it. Yes. Thanks for watching.